Whenever light strikes the surface of an object, electrons begin to move within that surface of that object. And that's because the energy within the photons of the light is transferred into the kinetic energy of those electrons. And this phenomenon is known as the photoelectric effect. So let's look at the following example, which is essentially a biological application of the photoelectric effect. So visible light, which is the electromagnetic radiation that is detected by the human eye, ranges from a wavelength of about 400 nanometers to a wavelength of about 750 nanometers. So using this information, we want to estimate the minimum quantity of energy that is required to initiate the chemical processes on the retina of the eye that enable us to actually see. So let's begin by looking at the following diagram. So we have the retina of the eye that is found in the back of the eyeball of the human eye. And the photons essentially collide with the electrons found on the retina of the eye. Now, photons are basically units, discrete quantities that carry energy. And the energy is a function of the frequency of vibration of those photons. So basically, the smaller the frequency is of our vibration of the photon, the less energy our photon carries. So, because we're looking for the minimum quantity of energy that our eye can detect, we must find the smallest frequency that the retina can detect. So this corresponds to the highest wavelength. So we know because this is the range that is detected by the retina of the eye, we're looking for the highest wavelength, which corresponds to the lowest frequency. So recall that the speed of light in a vacuum given by c, which is a constant, is equal to the product of the wavelength and the frequency. So because we know what c is, and because we know what our wavelength is, we can solve for the frequency. So we want to calculate the frequency that corresponds to this maximum wavelength. So the frequency is equal to c divided by lambda, where c is 3 times 10 to the 8 meters per second, and lambda is 750 times 10 to negative 9 meters. And that gives us the meters cancel, the seconds goes on the bottom, and we have 4 times 10 to the 14 seconds to the negative 1. So this is the frequency. It's the number of vibrations our photon makes every single second. So now we found the minimum frequency. So now we can use that to calculate the minimum energy that our photon can carry and still essentially cause that chemical process on the retina of the eye. So the minimum energy is equal to h multiplied by the minimum frequency, which was calculated in this section. So this quantity multiplied by h, Planck's constant, 6.626 times 10 to the negative 34 joules, multiplied by seconds, the seconds cancel, and we're left with an energy of 2.65 times 10 to negative 19 joules. So because we're dealing with microscopic quantities, we have to convert joules into electron volts. So 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. So we take this quantity and divide it by 1.602 times 10 to the negative 19 joules per electron volt. The joules will cancel and we're left with about 1.65 electron volt. So this is the minimum quantity of energy that is required by the electrons found on the retina to actually initiate the chemical processes on the retina that enable us to see.